Hey, howdy everyone. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I work in, teach, and conduct research in data analytics, machine learning, and geostatistics, mainly focused around spatial problems. Now, this is getting very close to the end of my machine learning course, and we're getting into artificial neural nets. What I'd like to say here is that I really have tried to make this content accessible, and I think this is really fun. This lecture is fun because often artificial neural networks are seen to be a bit complicated. Let's see if we make this accessible and fun to a student, an engineer, a data scientist, a geoscientist, any type of scientist to be able to understand this topic. So, what's the motivation? Well, this is a very powerful nature-inspired computing methodology that we can use for making predictions. Very, very powerful methodology for machine learning. I love the nature-inspired approaches. The idea philosophically that nature has evolved great solutions over billions of years, and that these solutions can be used by us to solve problems in a numerical realm, to me just blows my mind. I think this is a really, really cool thing. So let's go ahead and talk about this topic. We're going to look at this specific form of nature-inspired computing, and it is based on the idea of higher order like mammals and their brains that have sets of nodes that are also known as neurons in the brain that are highly connected with each other by synapses. We're going to work computationally with artificial neurons and artificial synapses, or I'll just call them connectors from now on. And what we'll find is that by having many nodes that have very, very simple processes, they're not very smart at all, but all of them interacting with each other, the result is that intelligence emerges from that. Well, this is getting a little metaphysical now, but we'll see. The model will be able to fit very complicated phenomenon by using a highly connected set of very simple processors. Now, just a reminder, this is machine learning prediction. We're just simply building a model to predict a response feature from a set of predictor features. Supervised learning, we're building prediction models with data set that are already, we know the response, we're training with those data, we're trying to minimize the error. This methodology is highly nonlinear. We can capture and predict very complicated features. In fact, it's so flexible, we're going to call it a universal function approximate. What we will say is that this methodology is able to learn really any possible function because it's so flexible. Okay, so for the rest of the lecture, this is going to be our friend. This is going to be our very simple artificial neural net. We will have a single hidden layer right here. It will be feed forward, so all of the information is passing from the inputs, the predictor features, to the output, the response feature in this direction. All of the connections, all the information just flows along in this direction. I got the direction right. It's feed forward. Okay, so that's going to be our artificial neural network. Let's go ahead and break it up and talk about all of the pieces associated with it. It's going to have a whole bunch of connections. Those artificial synapses are just going to be these connections. Now what you'll notice immediately as I color code it between the layers, that the connections are going to go from one layer to the next layer, and it's a fully connected system. In other words, the full combinatorial of connections are made between the layers. This node here is connected to every one of the nodes here. You see that? I'm going to show you later, it's passing on the same information to all the nodes, and then this node here is connected to all of the other nodes, and so forth through how many nodes we may be dealing with, which would be the width of our neural net. Okay, so it's fully connected, feed forward, those are the connections. Okay, now let's talk about the nodes. And what I've done here is I've just removed from that hidden layer in the middle of our neural net, I removed all of the other nodes so we can focus on Z1. No mystery here. If you go back, Z1 was right there. Now we come back here and you can just see we're focusing on that one node. What that node is going to do is going to take a linear weighted combination of all the inputs coming from the previous layer, all the nodes in the previous layer, And then it's going to non-linearly transform it. Okay, it'll transform it and get a new value, and it will pass that value on to all of the nodes fully connected again in the next layer. And what's going to happen is that's a very simple processor. It has a set of weights. We'll also put a bias term in, and I'll show that. And then through many interconnected nodes, all having that very simple linear weighting with bias nonlinear transform, we're able to now be able to model very complicated features, very nonlinear type patterns, and so forth. Okay, so let's go ahead. We've been kind of dancing around it for a little bit. We'll label each one of these layers. So we have an input layer. We got our predictor features coming in to each one of those nodes. Now we could have done some type of expansion, and that's often done, but we're not going to talk about that here. We'll just go ahead and take all of our predictor features and pass them in. We got a hidden layer. It's hidden because it's not exposed to the outside of the neural net. It's got an input layer and output layer. It's sandwiched in between. Not a big deal. Now, the one thing that is really cool is if I was to design my neural net with more than one hidden layer, I can update my CV and say I'm doing deep learning, because that's what deep learning is simply multiple hidden layers. Seems not too big of a deal, but we'll just leave it there. And output layer is going to be the nodes that are exposed to the predictions, the response feature that coming out on this side. Now, you'll note I put an arrow here. I indicated that there could be 1 through k. So there could be any number of outputs coming from this model, predictions, and they could be actual values, or they could be probabilities in the case of classification, and so forth. So that's going to be the separate layers. It's feed forward, fully connected. Everything passes from every node in each layer to the next layer, to the next layer, and it steps through my model. Now, we should mention this, that we're going to do normalization. Now, we've already covered min-max normalization. We commonly used the 0-1 normalization. It's very common with artificial neural nets to use a -1-1 normalization of all of the inputs, the predictor features, and the response features. The reason we're doing this is to remove the influence of the scale differences between the predictor features. We've had this problem before, this same. But more importantly, we want to get the values in the right range so that when we apply the activation functions, we get the optimum sensitivity. If we were to work way on the tails of the activation functions, well, some of them are bounded and there'd almost be no effect at all. And so we want to improve stability of the solution and sensitivity. So we're going to do everything in normalized space, and we'll back transform to get back to the original feature space on the other side. So now what we'll do is we'll walk through our neural net. We're going to follow one path. We're going to go through one node in the hidden layer and come out on the other side. So let's go ahead and walk through this step by step through our very simple, fully connected feed-forward artificial neural net. Okay, so let's walk through. We're going to start with the min-max normalization of the predictor features, and the result is we have now populated the input layer nodes of our neural net with just those values. That's all we've done. Okay, and we've done that to once again improve the activation function sensitivity, remove sensitivity to differences and variances or ranges of our predictor features. Now what we can do is we'll go from that input layer and we'll take all of those values and we'll go through one specific, the Z1 hidden layer node. And when we do that, what we'll find, it's not a big deal what happens inside that node. Inside the node, we're going to calculate that Z value that'll be passed on. The Z1 value that'll be output will simply be a function of a bias term at that node and weights applied to all of the inputs coming in. Now, this isn't so bad. We'll apply a nonlinear transform. That's what our function is going to be. We'll talk about that shortly. We should also note that this bias term could be unique to the node, each one of the individual nodes in a layer, or it could actually be common or shared among all of those nodes, and both could be possible. Now, we should indicate that that f function really is a sigma function, which is going to be our activation function. Well, we'll mention later on we could also call it a transfer function. in which it's going to be a nonlinear, a very simple elementary nonlinear transformation to impose a nonlinearity into the system. So we got a linear combination, weighted combination of the inputs. We add a bias term. Then we go ahead and apply a nonlinear transform, a very elementary nonlinear transform. We'll talk more about activation functions just in a little bit. So the result from that will be the nonlinear transform bias plus linear weighting of the inputs coming from the input layer. Then it's going to be passed on. That same value from Z1 is going to be passed on to all of the nodes in the next layer. It's a fully connected feed-forward system. It's going to pass that same value to all of the nodes. Okay, so they're all going to see that same value. They're going to gather up all of the values from the other nodes, and they're going to then deal with those values. Okay, so what happens at the output layer? Well, we could actually take the hidden layer and just repeat it and say, well, we think it'll be another transform of a bias term plus linear weighting on all of the inputs there. And that would be true. Now, the one difference is most of the time for the output layer, if it's regression, what we'll do is we'll just use the identity as a transform. In other words, GK at that kth node, transform of the bias plus linear weighting will just be equal to that result. It's identity. So we're not doing a nonlinear transform again. The other thing we'll do if it's classification, we'll use this term right here. Now, if you look at this transformation, very straightforward. It's constraining the values to be greater than 0 and the sum to 1. That way we ensure that we have closure and we have actual probabilities. And so for classification, what we want is a probability of each possible category. So we'll apply that to make sure that we have probabilities. Okay, valid probabilities. So then once we've got that value, then we're going to do a back transformation and we'll get it back to the original predictor, the original response features values. And so we'll do that. Now we'll apply that transformation for the case in which we're dealing with regression problems. Okay, so now we'll talk about the parameters that we'll have in our neural net. And one statement I often make is that non-parametric machine learning is often just parameter rich, and machine learning excels at that. There are many, many parameters. And so we had all of the weights for all the combinations in the hidden layer coming in from the input layer. We have all of the weights for all the combinations from the hidden layer to the output layer. And so for a fully connected feed-forward system, the number of weights is going to be P, the number of nodes in the input layer, times M, the number of nodes in the hidden layer, and the plus the number of nodes in the hidden layer times the number of nodes in the output layer. That's a total number of weights we're going to have. That's the full combinatorial. And then in addition to that, we're going to have M and K bias terms if they're going to be unique to each one of the nodes in the hidden layer and the output layer. So that, in fact, if you imagine for many practical artificial neural nets, that's a huge number of parameters that we're going to be training. That's a parameter-rich model. Now let's talk a little bit more about the activation function. It's going to be a nonlinear transform of that linear combination plus the bias term of all of the inputs coming into the node. It's going to introduce nonlinear properties to the network. Without the activation function, in fact, we would just have a linear system, and increases the power to learn complicated patterns. It's also known as a transfer function, as I said before, and because of this, we're now able to have what we can say is a universal function approximator, that we should be able to fit almost any form. We have enough training data and we build our neural net well, we should fit almost any system. Now let's talk about activation functions. I went to Wikipedia and grabbed this. This is the threshold function, Heaviside step function. If you look at it, it's a very simple activation function, probably the simplest one we can imagine beyond identity, which would just be a linear function, right? And so what you can see is a threshold. If the input is above a certain value, 0 in this case, it will go to 1, otherwise 0 output. And so this, if we were to build a neural that was single hidden layer using this type of model, it'd be only capable of linear decision boundaries. In fact, here's an example taken directly from Wikipedia. Maybe you have cases of size and degree of domestication of animals, and you're trying to determine whether or not they're a dog or a cat. I'm not going to take any sides on the whole dog-cat issue, okay? Now, what you'd imagine is you'd only have a linear boundary if you were to use this type of model. It'd be very, very simple. And if you change the bias term, which is really interesting, kind of instructive, it wouldn't change the slope, it would just change the location of the boundary. Okay, so, but let's go to more complicated types of models. And so what we have here is we have an example of logistic, we have tan-H, and we have ReLU right here. And so if you look at them, they in fact, I hope I can convince you, they are very, very elementary nonlinear functions. They have, in general, tan-H has pretty strong gradients right near 0, and then it starts to level off and it loses sensitivity. And this explains once again why we did the min-max normalization on our inputs into the model. We can have discontinuities too. Here's linear with another linear component with no sensitivity at all. And so we can have a variety of different functions that we work with. Now, let's make a couple of comments around activation functions and how we select them, some considerations in selecting them. Now, here I'm going to confess the fact that this is not my expertise. I don't have a huge wealth of experience in building these models where I can draw on, but I'll just make some general comments here. Nonlinear. Well, we need nonlinearity in order to, in the function, to impose nonlinearity into the system. In order to get a universal function approximator, we need them to have nonlinearity. The range, they can be either be finite for more stable gradient-based learning, or they can be infinite. More efficient training, they have more power over a wider range, but we may require a slower learning rate to improve the stability. They can be continuously differentiable, and really that's what's required by theory for stable gradient-based optimization, and we would expect them to be monotonic. By doing that, we have guaranteed convexity for the error surface for a single layer model. And so this will improve our chance of finding a global minimum for our loss function. In other words, training our model to get the very best weights to minimize the error of the model with the training data. Okay, so how do we train a neural net? Well, we're going to have a lot of parameters. We already mentioned that there's going to be a parameter-rich model. We got to set those parameters. The way we build the neural net, actually kind of interesting, is we're going to set the original parameters to random, kind of close to 0, random. And then we're going to do a forward pass run on our neural net with the training data. And what we can do from that is we want to calculate some concept of rate of change of the error versus rate of change of the weights. And if we can do that, now we know how to iterate or improve our weights. Now this starts to sound like a gradient problem, and it is. We're going to do a gradient optimization again. And so you can go back to the lecture on gradient boosting where we start to get into that a little bit. Now note, in setting up this problem, we're going to recognize that T is going to be all of the other assumptions like activation functions, number of nodes, number of layers, hyperparameters. And so these are going to have a strong impact on the performance of the model. Okay, so let's go ahead and talk a little bit more around this. We got to define some performance or loss function we want to work with. We can say P is equal to a L2 norm, and we've already talked a lot about norms. And so across all of our training data, 1 through n, we could summarize the residual sum of squares, the differences in the performance of the model versus the estimates that are being made. We could also consider the averages and so forth. There's a variety of ways that we could express error, but we'll just leave that as P, the performance of our model. Now, what we really want to do, if we want to understand the model and how to update all of those weights or parameters of the models, we want to be able to calculate what is this, for all of the possible weights, what is the partial derivative of the performance of the model versus each one of those weights. That's what we really, really want to work with. Now, if we had that, then we could figure out how to update each one of those weights. or each one of those parameters of the model. And in fact, what we'll do is we'll do gradient-based optimization. We want to go in the direction of steepest gradient. So we want this is going to be our gradient. And we're going to want to make updates based on the concept of scaling by a learning rate, like we did before in boosting. We don't want to just go and correct everything, boom, really fast. For the best model possible, we want to accept the fact that our model will move slowly. It'll be more stable like that. Okay, so we're going to go ahead and update all the parameters. So I could take a single example of a weighting term within our hidden layer, an alpha, and I can say that it will be equal to itself minus the learning rate applied to that gradient, steepest descent gradient. So this is really powerful. This is very useful. This is what I want to calculate for every one of the parameters of the neural net. And there's a whole bunch of them. It's going to be a bookkeeping nightmare. And we're going to go ahead and calculate that for the model and know which way to adjust the model. Now they call this back propagation. The reason being is that it's obvious we can calculate the partial derivative of the performance of the model relative to the output of the model right here. That's just going to be the error of the model. Now what we need to do is we need to actually propagate that error back through the neural net. And so that's why we call it back propagation. We want to partition that error through all of the model parameters. In fact, we want to go back to the beta parameters of the weighting terms in the output layer. We want to calculate what's the partial derivative of the performance of the model, i.e. our L2, our norm, the error of the model summarized, versus all of those weighting parameters within the output layer, the beta terms. Then we want to calculate the partial derivative of the performance of the model relative to all the weighting parameters in the hidden layer. But what's interesting is the partial derivatives of these values is going to be dependent on the subsequent layers afterwards. So that's why it's back propagation. We have to solve here, then we can solve here, then we can solve here. We got to step through in order to solve this problem. One way to see it is we're distributing the influence of the error across all of the model parameters, back propagating. Okay, very cool. How are we going to accomplish this? Not too bad. We're going to use the chain rule. Why? Because we got to move through those nodes. We got to move through the activation functions. We got to go through a lot of stuff. And so we're going to need the chain rule in order to do that. So remember the chain rule, that if I define a function of a function and I want to calculate the derivative of that, what I'll find is that I can simply solve for that by taking the derivative of the outer function, ignoring what was going on inside of it. Ooh, I forgot a bracket. And then multiply that by the derivative of the function inside, the g derivative. Okay, now why do we care about that? Well, just look at our problem right here. We got a linear combination of weights plus a bias term, and then we got a nonlinear transform for that. So clearly we're going to have to solve nested functions in order to get this. Okay, so let's go ahead and do that. So we're going to use the chain rule to move backwards through the network. Now, we're in a situation where we already know this right here, the performance, the partial derivative of the performance of the model versus the output here from this node. That's the prediction being made from the model. What I want to do is I want to back propagate to the input into that node before the activation function was applied. And so by the chain rule, you can see that the partial derivative of this input into this node is going to be equal to the partial derivative of the output to the input, the product of that with the partial derivative of the performance to the output. And so I can solve for that. In fact, what's really interesting, I already have this. I know the partial derivative with regard to the performance of the model for the output. And I just need to solve this part right here, which is going to be the partial derivative of the output to the input, which in fact is just simply going to be the derivative of the activation function. Now, spoiler alert, design has gone into the activation functions to ensure that this is easy to calculate. In fact, the sigmoidal activation function, its derivative is simply itself times 1 minus itself, which is Super cool. Really, really fast to calculate because we got to calculate this many, many times. Remember the part where high parameter count and this is a bookkeeping nightmare? Yeah, there's going to be a lot of times we're going to need to calculate this. Now, but that's not good enough. Really, to get interesting, I need to get back to these parameters right here. The weights applied to each one of these inputs into this node. That's more interesting, right? So let's go ahead and back up even one more step. And so what I want the partial derivative of the performance of the model relative to this weighting right here. And I can solve it with the chain rule as the partial derivative of the input given that weighting multiplied by the partial derivative of the performance of the model given the input. Now remember, we've already solved for this part, so we can actually add that in. Remember, we did this last time. That's the right here. So you see we're just chaining it together. We're moving back through the neural net. Super awesome. Okay, so how do we solve this? Because I think it's really insightful to kind of just explicitly say how we'd solve for this partial derivative performance relative to that weight right there. Well, it's going to be equal to this term right here. And if you think about it, that's the partial derivative of the input given that value right there, which is simply going to be equal to the z value that's passed on because it's this multiplied by the z value. So we'll be left with that constant, the z value. So it's just the z1 value. Super awesome. This derivative right here is just the derivative of the activation function, and this derivative right here is simply going to be the prediction error in the model. So using the chain rule, we backed up and we got all the way back to this first set of weights. And we can solve for that. Now, not a big deal. We could do both of them, the B11 and the B12, and we could get their rates or their partial derivatives of the performance of the model, which we've already said before is the gradient that we need to move in to go steepest gradient to solve for the very best weights. And so we can solve for it using the chain rule. Now we'll keep backing up through the system, and I have to admit I got a little lazy. It's going to get filling up the whole slide to kind of put it all in. The one thing that gets a little bit complicated is when we start getting over here and we start thinking about what types of weights we could change here if we had a multi-layer type of neural network and so forth, that now we're in a situation where there's multiple paths by which we influence the prediction. And so we got to keep track of all of those paths. We haven't had that problem so far. Not a big deal. So there's going to be a bunch of chain rule and a bunch of addition of different paths. Okay, let's talk about how we actually accomplish training. We've already said we're going to do steepest descent, and we need to calculate the partial derivatives, know that those gradients to do the gradient-based steepest descent. We're going to do it iteratively, and so we'll have epochs, which sounds very geologic. And so an epoch is one forward pass and back propagation applied to all of the training data. That's known as the epoch. We may have actually multiple batches in doing that. And so what is a batch? It's a number of training data considered in each forward pass back propagation iteration. And so let me just give you an example. If you have 1,000 training data and your batch size is selected to be 100, you would require 10 iterations of forward pass back propagation to complete an epoch, because an epoch is when you've gone through all of the training data. And we're going to do many epochs over which we'll iterate, and we'll keep improving the parameters of the model doing that. Now, let's make some comments here. Larger batches result in a better estimate of those partial derivatives, that is the error, but slower epochs, more computation, so more computational time for every one of those iterations. Smaller batches result in noisier estimates of the error, but faster epochs often resulting in faster learning or even possibly more robust models. And for the most important point, this is it right here, and I won't get into the details. Smaller batches often result in models that are better able to generalize. Now, generalize is just saying we have a model that will do the better job in predicting with new observations not used within the training, i.e., we're not in a situation where we're potentially overfit, and we have a model that's going to perform well in testing, but also real-world use. Let's give a couple more comments around this idea of iterative type of approach, a gradient descent. Well, when we're working with gradient-based optimization, we're always concerned about issues around getting to a good solution, finding the global minimum, not getting stuck in a local minimum. And so there's a variety of hyperparameters that we can use to improve the this optimization. Learning rate, as I mentioned before, we're going to use that to regularize the rate at which we update or change all of the model parameters. The main idea with that is we want to make sure we don't jump across or skip over a global maxima. We want to ensure that we find that. Momentum is kind of the opposite. We don't want a gradient descent that starts to just oscillate back and forth and become very unstable. And so we're integrating memory into the vector, the direction by which we're going. And so the update we're going to make is going to be a function of a weight applied to the previous update plus the new information that tells you how you want to update given this current iteration. And so this is a nice idea. So if you imagine traversing some space, it prevents you from oscillating back and forth. It forces you to kind of have a limited curvature. You have to kind of keep going in the same direction. Momentum, it makes sense. Now, there's a whole variety of other hyperparameters. I mentioned learning rate and momentums. The performance metric, in our case, we were just working with an L2 norm. The width of the artificial neural net, the number of nodes in each layer. The depth of the artificial neural net would just be the number of hidden layers. In our case, the activation functions, I gave a couple of comments around how you would pick one without any claim of any high level, or I should say kind of deep expertise in that. And the output function, that's kind of given. It's going to be identity, or we'll transform it to force a closure and valid probabilities. Some limitations of neural nets. Well, I love this, the no free lunch theorem. I spent much of my grad school, actually much of my life looking for free lunch. There's actually quite a few times you get free lunch as a professor, which has actually been really nice. Thank you very much, University of Texas at Austin. We cannot guarantee the model is always optimum for predicting new unobserved cases. We could sit back now, we could talk about black swans, we could talk about overfitting and so forth. But it does make sense that we can't guarantee the model will always perform well for all possible cases. Parameter rich requires a large number of training data. I'm old-fashioned that way. I always say, well, go back to the original concepts of degrees of freedom. What's the total number of information you have? And what's the total number of assumptions you have to make? And if you're negative, you're in trouble. So we're going to need a lot of data to train this. Low interpretability. Generally very difficult to interrogate the model. You got all of these weights. It's hard to figure out what they mean. And high complexity models results in probably higher model variance and lower model bias than what we're used to in many other methods. There's a whole variety of different architectures around artificial neural nets. Deep learning, where we use many or multiple hidden layers. Recurrent neural net, where we actually have information pass backwards within the neural net. That's fascinating because it actually creates memory in the system. And there's long short-term memory systems which actually filter out more short-term type of information versus long-term patterns. These methodologies are quite successful when working with temporal information, which would have, make sense to kind of learn and accumulate over time. All right, and convolutional neural nets are a artificial neural net that's been more designed to mimic what happens with our visual perception and our visual cortex. This idea that if you look across your field of vision and you look at it, you aren't seeing all of it at once. In fact, what your brain is doing is breaking it up into subsets. And then what it's doing is identifying salient features, let's say outlines or movement. And then it's taking that, summarizing, going to a different scale, rescaling it, and repeat. And that's what convolutional neural nets do. And because of that design, they do a very good job at working with image information. And autoencoders, which are used for things like dimensionality reduction. There's so many different things that we could be talking about as far as artificial neural nets. This effort was just simply to scratch the surface. Now, I have an artificial neural net example, a prediction model that could be used on seismic subsurface information. I'll record that lecture later, but for now I'll stop right there. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, where I teach and work in the topics of data analytics, machine learning, geostatistics. And if you want to hear more about my research, if you want to work with us and our students, we're open for business. We're working with a large number of different companies in trying to help with new solutions in this area. And so it's great. I love the partnerships, great for the students. supports the students, and great for the companies. Everybody wins together. Very collaborative. My attitude is that we work closely with companies because we will all benefit from that collaboration. All right. If you want to hear more about my content, go ahead and check me out on GitHub, where I have a repository, Geostats Guy, with all of my workflows, tons of examples, tons of demonstrations, even demonstrations in Excel of doing a bunch of data analytics in case you want to start out somewhere like that. I also have this YouTube channel, and I have Twitter. I'm Geostats Guy on Twitter, where I put out a lot of content every day. I try to share positivity. In fact, my goal in life is to build, is to make, and try to help people and be a voice for science, and I hope I'm accomplishing that as well as I can. All right, I hope this was helpful to you. Take care.